Let's try to work through the math now and really think about what's happening mathematically in our interference. So the first thing is to go back and remember that phase difference is a really helpful way to capture this. And phase difference was typically going to be related to our omega t, our kx, and then our initial phase constant. Now, when we then subtract them and think about the difference between two of them, for one dimension, we said that omega t, we didn't have to think about the difference as long as these have the same wavelength or the same frequency, which they do. But then we do get a difference in x just due to path length difference, that our source is not in the same location. And then potentially there is a difference in initial phase. So we have a similar thing now, but we're actually generalizing what was before delta x, representing the difference in where they're placed, to be delta r. And the reason for that is if we pick some random point, we have one distance to one source and we have a different distance to the other. And now these are two-dimensional or potentially three-dimensional, though we don't typically do it in 3 dimensions. So recognize that delta r then is this path length difference generalized to be in 2 or 3 dimensions. So then our condition otherwise is really similar to what we had before. Maximum constructive interference means that the overall phase difference is going to be an integer number times 2 pi, where this integer could be 0, 1, 2, and so on. This can be coming from just a difference in path length, but also a difference in initial phase from our two sources. Destructive interference is going to be when you have an integer and a half multiplied by 2 pi. So again, this gives you, for instance, a cycle plus a half. So for instance, your crest plus your trough would be giving you your destructive interference. So to try to think through what's going on, we can simplify this a little bit more. This picture still had these phase differences, so there's no reason that our two sources have to be in phase. This picture here actually is showing them in phase, and the reason for that is notice that for both of these, you pretty much have one wavelength spacing between the source and the smallest circle. And so what that means is we are in a moment where the source is putting out another crest and they are both putting out that crest. So if you had them not having the same phase, that would be like all of your blue circles being a little bit smaller while the green circles stayed the same size. And that would correspond to the blue circles being closer to the source, and you would see then that your locations of constructive and destructive interference would actually move a little bit. So let's instead think about identical sources. This simply means that they have the same phase, and that again is the picture we've been talking about. It isn't necessarily important that the source is on a circle from the other one, as these appear to be, but again, the fact that the smallest circles are of the same size indicates that they are in phase. So once we drop that phase difference, we then can think simply about path length, where again we're talking about a two-dimensional path length, so we call it delta r. An integer number of wavelengths is going to give you a constructive interference, and then an integer half number of wavelengths gives you destructive. So what this picture is trying to show you, if we look at point A, that's where two circles are crossing. But it's actually 3 wavelengths away from your green source and 2 wavelengths away from your blue source. However, the difference in path length is 1 wavelength, so that's a point of constructive interference. If we look at point B, it's 3 lambda, 3 wavelengths away from the green source. It's 2.5 away from the blue source. It's in between the two circles. So this is a point of destructive interference. Now, let's then look at point C, which hasn't been done, but this is an interesting example. If we look at how far away it is from the green source, this looks to be lambda over 2, right? It's half a wavelength away. If we then look at the blue source, it's 1, 2.5 away. So this is 2 plus 1/2 lambda. Now what's tricky here is that you see lambda over 2 and another 1/2 over here. But remember that we need to take the difference. And so for point C, if I take what my difference in path length is, that's actually 2 plus 1/2 lambda minus lambda over 2, which equals 2 lambda. So in this case, that is actually this model here. And remember that we also said that if your point is in between the circles, as it is in this case, it's perfectly in between your blue circle. It's also perfectly in between the source, which is at a peak, and the first circle. So this is a trough and a trough. So even though each distance has a 1/2 in it, remember that this must be a difference. So if you subtract two numbers that both have a 1/2, you get back to an integer. So I hope that this is clear. Again, thinking about path length can be really helpful because you're going to have many problems where you need to do this quantitatively. I do always encourage you to draw a picture, and remember that we have to talk about path length difference, not just absolute path length. So lastly, we saw before that our points seem to fall in lines, and these are actually nodal lines that have a fixed distance between these two positions. And depending on how good your pre-calculus is, you might recognize that there are certain specific types of shapes that will result in the distance always being a fixed relationship between 2 points. But so notice, for instance, this black line here is always a 3/2 lambda difference in path length between the blue and the green. So this is going to be a destructive interference location. And we can just pick one spot to look at this. So for instance here, and notice that at this point it is on a blue circle, but it is in between the green circles. So from our logic before, when we just were thinking about circles, peaks and troughs, this would be destructive interference. But when we know that the path length difference is 3/2 lambda, this corresponds to an m plus 1/2 lambda, which was our destructive interference situation. You can see that a red line, such as this one, hits everywhere on circles that intersect, but you also have places like this in the middle that's in fact in between both circles. So this red line still includes some locations that are trough and trough. Notice that as you change the spacing between our sources, the overall shape of the lines will stay very similar, but if we make them farther and farther away from one another, you're going to get more and more lines in between them. So do keep in mind that the exact pattern here does depend on the spacing between the sources, but in general, these are the sorts of shapes you get. So we call the red lines antinodal lines. Those are places where you always have constructive interference. And we call the black lines the nodal lines, which is where you have destructive interference. So remember, nodes mean you have 0, and antinodes means you have maximum values. And again, this is the shapes that you get.